Hi everyone, welcome to another episode of my tutorials on RNA Seq data analysis. This is the second episode in the series where I show how to run the DESeq2 on your PC to analyze RNA Seq data and identify differential expressions. So if you want to watch the previous video, in the description box you'll find the link to watch that video. I also have tutorials that show how to run the DESeq2 on Galaxy, so you can also watch that as well. So just check the description box, you'll find links to all the videos you need. All right. Now, for this tutorial, the R script that we are going to use, the script which has all the codes, it's available. So if you want it, check the description box, you'll find the link to get the script. Now, for this tutorial, you need to make sure you have R installed, and you should also have these R libraries installed. DESeq2, Heatmap, and then R color brewer. So make sure to do that. Now, let's take a look at the example data we will use for this exercise. So I have the data on one of my GitHub repos. This is a page, and I'll leave the link to this page in the description box. So make sure to download these files, design.tsv and then raw count.tsv. All right, so make sure to download them. These are going to be our inputs. I already have the data on my PC, so I will show you. I want us to examine these files before we start the analysis. So I'll start with the raw count.tsv. You can open it with any spreadsheet software. So I'll open mine now. All right, so it's open now. Okay, it has been opened, but I'll enlarge it a bit. Yeah, I think this should be better. I'll just make it clear so that we can all see. Let me do that now. Okay, so the first column has the genes, and then the second column up to column number 7, these are samples. So we have the sample IDs or sample names, whichever one you want to call it. Each row represents the record for a gene, i.e. the read counts. So if you take a look at this one, for example, DDX11L1, this is a gene. And so what we see here are read counts, okay? Read count that were obtained from the various samples. So this is the gene. In this sample, the read count was found to be 8. In this sample, it's 11, and in that order. All right, so this is the data we are going to use. Now, for read count, you can use tools like DESeq, feature counts, etc. And I have a tutorial on feature count. So if you want to learn how to generate read counts, just check the description. You'll find a link to that video. All right. Now let's do this. This data was obtained from this study. Let's look at the study also. Here's the study. So in this study, the authors identified this long non-coding RNA LETS1. They found that it promotes TGF beta-induced EMT, and then cancer cell migration by transcriptionally activating this particular stabilizing mechanism. All right. So just visit this page. Okay, the link to this page in the description so that you can read more about it. The data is also available here. You can come to the geo database and then search using this accession ID, and you can get the data. You can also analyze this data online. You don't need to download and analyze. You can do it on the Geo2R server, which is here. I already have a tutorial on that. So if you want to learn how to use the Geo2R to analyze data, which is already on the Geo data sets database, then just check the description. You'll find a link to that video as well. All right. So that's about it. So here the authors overexpressed this long non-coding RNA, the LETS1. They express this in some cells, and then the total RNA for those cells were isolated, and then that was used to generate the data we are going to analyze. Okay, of course, controls were also set up. So this leads me to the sample information. All right, I have that here. It's called design.tsv. So I'll open that and we'll look at the samples. So I have that also here. Let me enlarge it a bit. Okay. So I have the sample ID. So you have the samples and then the groups that they belong to. So you have the control group. You also have the TGF-beta. So the TGF-beta, these are the cells in which the LETS1 was overexpressed. Okay, so we have the cells here. Okay, these are the cells. All right, so we have the control and then the other group, which has the overexpress, the measurement for the overexpressed LETS1. Okay, so we have two groups here. Okay, now you should take this, you should note this. Your sample information, the number of samples should be the same as what you have in the raw count if you are going to analyze. All right, so you should make sure they are the same. So here it's 6, here it's also 6. We will do some exploration in R by the way, but these are things you have to check before you start, otherwise you will run into problems. And the IDs should be the same, it should be consistent. Okay, so it should be the same. What you see here should be the same as what you see here. Okay, and they should correspond. All right, so you need to check all these things before you run DESeq2. Okay, so ladies and gentlemen, let's start exercise. So I'm going to open my R and then we'll start. Okay, I have opened my R environment. So I will create a new script. So I'll come to File, come to New File, and then I'll click on R script. So this will open a new script for me. Now I'm going to use a skeleton script which has all the activities we are going to perform. So I'll switch to that one. Okay, so there's a script. It has all the steps. So this will guide me. Okay. Now let's do this. We will start by loading the R libraries. So we will start with DESeq2. So I'll say library, the spelling, and I'll say DESeq2. DESeq2, if it's there, will be displayed for you automatically. So you can just click to select, and then you can execute this command to load the DESeq2 library. Okay. So we can see it's being loaded now here. So we can just check and monitor the progress. Okay. So the next library to be loaded is Heatmap. And by the way, the DESeq2 library has been loaded. So let's move to Heatmap. That is Heatmap. That is here. Right. So let's execute this command. It has also been loaded. So we can load the third one, which is R color brewer. So there's it. Let's load that also. It has been done. All right. What we need to do next is to set our working directory. Now the working directory should be the directory which has the data, the input files. I have mine here. So I'm going to load, and then I will set the directory which has these files. Okay, that's what I'm going to use. So I'll move back to R, and then I'll set it. So I'll say set WD, and that'll be /home/combiner/DESeq2. Let's type it properly. This is it. Okay, so now let's execute this command. Nice. We have set the working directory. So now we need to read the count data. So to read it, I'll say count_table, and I'll say read.csv. Like this. And I'll say raw count.csv. I'll indicate something else. So that will be sep equals /t. Right. Now the read.csv function is used to read text files. Okay, but it assumes that the text files will have a delimiter or separator of comma, because this is a CSV function, read.csv. And because we are dealing with a CSV file, which is tab, we need to specify the separator, and that is /t. So that is why we have to specify this. Now let's add another information. So we'll bring a command, we say row.names equals 1. So the row.names will be used to set the first column as the index, which in this case is the column which has the gen name. So let's execute this command. All right, that has been done. So now you can even do a head count table to see the data. You can also do this. You can say dim count table to get a dimension. This is a table. So the number of rows and columns. So the rows here represents the number of genes. Columns here represents the number of samples. All right. So that's what we have. Now we need to load the sample information. All right. So that is here. So that's reach the sample information. So I'll set that here. Okay. So you will say sample info and say read.csv quotes, and I'll say design.csv. So the same format sep equals /c row.names equals 1. So we'll set it like this. It has been done. So we can explore, you can say sample info to see that. So we have the groups, control, TDF-beta, and we also have the sample like this. Okay, this one here represents the index. Okay, so we have done that. Now let's proceed. Now before I proceed, I will also get the dim again. So I'll say dim into brackets sample info. So we see that it's what? 6 by 1. So that's 6 rows and then 1 column. All right. That's what we had here. Okay, so there's the column group. All right. Now I made mention about the number of samples in the design file matching with the number of samples in the count data. So I'll just check again here. I'll say dim, right? Now say counts and I'll store table to see it. Right, so it's matched. So we have 3, 9, 3, 7, 4, 6. So this 6 and this 6 should match. That's what I earlier on explained. So you can also check that here in R. That's how you do it. All right. So now we can proceed. Okay. What we are going to do next is to set factor levels. That is this step here. All right. Now, what you need to know is that factors are groups or conditions that can contribute to the difference in gene expressions. All right. So if you take a look at our data, let's just look at it again. I gave a description earlier. We have control, we have TGF-beta. All right. So the TGF-beta group, these are the cells which has the overexpressed LETS1. Okay. These ones do not have the same treatment. They do not have the overexpressed LETS1. And so the difference in treatment can contribute to differences in gene expressions. All right. And so therefore, this particular group here, okay, this header here, which has the control and TGF-beta. So this becomes a factor. Okay. Now group, you can give it a different name. Okay, it's also fine, but for you to, we are just keeping that group. So we have the cells, okay, which has the overexpressed LETS1. These are ones we do not have. So that's why I'm using the word group. So in this case, group becomes a factor. Okay, so group is a factor, and then the levels are control and then TGF-beta. These are levels because these are all under this group. All right, so this is a factor. That is the header, and then these are all under that group. All right, so these are the categories. So under group, we have this and we have this. All right, so these are the levels, the factor levels, and this is the factor itself. So that's what you need to note. Okay, so that's it about factors. Now let's switch back to R and then set the factor levels. All right. Of course, if you have to set factor levels, we need to first create the factors. All right. In this situation, you have just one factor, so that's fine. So we have to make sure we have that factor object, and then we can now set the factor levels, and then we can proceed. So that's what we are going to do. We are going to start by saying factors. You say equal to factor sample info $group. Let's execute this command, and then the next thing we have to do is to get the groups. So we say groups equals unique sample info $group. Let's execute this command. So we are using this one because we want to eliminate duplicate. We want to remove duplicates. We want just the group themselves. All right. So the groups, let me just type it here. If I say sample info $group, I'll get control, TGF-beta, etc. All right. But I want to remove duplicates. I want just those groups. That is control and then TGF-beta. So that is why I'm using the word unique to remove the duplicates. So I have the groups. All right. Now the groups, let me just display it. It's control TGF-beta, right? But then when making some entries where we have to specify the groups in the DESeq2, the groups should be specified in such a way that the control group is the last. All right. So we will try to rearrange everything so that when we are listing it, the control group is the last to be displayed. And so I will issue this command. I'll do a reverse of it. So I'll say groups. I'll say rev groups like this. So now if I try to display groups, we should have TGF-beta and then control. So this is what we want. All right. So this becomes our final groups. And then we are going to use that to set the factor levels as well. All right. So what we will do is to first assign the factor objects that we created. I repeat, so what we are going to do is now assign the factors objects we created to the sample info table. So this is what we are going to do. We are going to do this. We are going to say sample info $group equals to factors. All right, because we are converting that to the factor object. So the factors here is just one factor, sample info $group, and we are assigning it to this. That means we are replacing the original group column with the information which is now a factor object. Let me just put it that way. Alternatively, we could have just brought this straight here. That's also another approach. So now we don't need to execute this code. We don't need to type this code and then come and type. We can just do it straight up. But I just want to keep it simple, step by step, so that beginners can understand whatever is going on. All right. So that's why I'm doing it this way. Okay. So anyway, I'll just do. So we can do it this way. So let's execute this command. All right. So now we have it done. Okay. So now if I type this, let me just do it here. I will do it here. If I do this, if I say sample info $group, I should have this display for me, right? So we have the groups and we have levels. So these are the factor levels, all right? So we have control, we have TGF-beta. So we are going to also do some correction. I made mention that the control or the reference should be the last to be specified. Here, it's not so, all right? But we are going to correct it when we are creating our DESeq2 objects, all right, to do the analysis. So we will factor that in very soon. Okay, some of these things you should always pay attention to it. Otherwise, you may end up getting wrong results. Okay, so this is it. So we are done with the factor levels. We've set it, so we can proceed. Okay, what we have to do next is to create a DESeq object. So I will do that now. So to do that, we'll say DDS equals, and I'll say DESeq data set from matrix, and I'll say count data equals counts underscore table. And I'll say call data equals sample info, and then design equals. So design here, we use it to specify the factor of interest. So in this case, it's group. So we say tilde. That's the name of the symbol, and we say group. Right. So this becomes the final command to create the DESeq object. So let's execute this command. All right, that has been done. Now you will notice this text here, this red text here. It's giving you some information. All right, it's telling you the recommended characters that you should use in your data. All right, so that's what it does. So it's not an error message. Okay, so don't worry about that. So basically, it's recommended to use these characters, okay, in your data. So it says it is recommended but not required to use only letters, numbers, and delimiters, okay, like this, okay, in your data. All right, but then we are using dash in our names. So if you take a look at the data we have here, the group, the TGF dash data here, so we have dash here and then beta, okay. So ideally we should just use letters. That's what I would prefer, okay, just letters alone. But what we have here, there's nothing wrong, nothing is going to happen, but it's just a recommendation. All right, okay, because sometimes these programs can behave unexpectedly because of some of these characters. So I always advise that you use just letters, but this one too will work. It's not a big deal. Okay, so let's proceed. So we have created a DESeq object. Now we need to set the reference for the group factor. Okay, we have our factor, that's the group. So we need to set a reference. So the reference here is a control. All right, so we need to set it before we proceed with the analysis. So that's what I'll do. I'll say DDS $group equals, that will be RE level DDS $group, comma, and I'll say ref equals control. So we will set this like this. So let's execute this command. All right, that has been done. Okay, what we are going to do next is to filter out low count gens. So that's what we are going to do. We are going to identify gens with counts greater or equal to 10. All right, and we are going to keep those gens if this observation, that is the gens having counts greater or equal to 10, if we should see that observation n times, then we will keep those gens. So n here refers to the size of the smallest group. Linking this to our data, let's take a look at the sample info table. We earlier on opened it in our spreadsheet. So there's a sample info table. So we have the group. Okay, we have the control group. We also have the TGF-beta group. Each of these groups has 3 samples. Okay, I repeat, each of these groups has 3 samples. So that means the size of the smallest group is 3. All right. Now let's go back to the R code. So what this ultimately means is that we are going to keep gens that have at least a count of 10 or greater. Okay, that has a count of at least 10. And then this observation should be seen in at least 3 samples. That's what it means. Okay, I repeat, we are going to keep gens with counts of at least 10. Okay, and the count of 10 should be seen. That observation should be seen in at least 3 samples. That is what it means. So let's put this in an R command. So this is what's going to happen. We are going to do this. Let's just enter that code here. So I'll do this. I'll say keep. I'll bring my equal sign. I'll say row sums counts DDS, right? And I'll say greater or equals to 10. So that means we are getting gens with counts greater or equals to 10. And then we come here, you say greater or equals to main table sample info group. Okay. The value of this is 3 because if you look at the groups, the size of the smallest group is 3. All right, so that's what this expression will give us. All right, so we are going to keep gens that have counts of at least 10, and then this observation should be seen in at least 3 samples. All right, so let's execute this command, and then after that we will subset its final. So we say DDS, and you say DDS keep. We are keeping those gens. That is what this means. So let's execute this command. Right, that has been done. So we can proceed. Okay, so we have done the filtering. So it's now time to perform the statistical tests. All right. So we are going to issue this command. So we will do this. We will say DDS, we say DESeq, we say DDS test equals word. That's what we are going to use. And then SF type, say post count. Okay, so the SF type is used to specify the method that should be used for estimating the size factors. Okay, so that's what we need to know. All right, so size factor estimation, okay, is used to make samples comparable. Okay, so in other words, it helps us to remove bias so that we can compare the samples and perform our tests. All right, so we are going to execute this command. Now you can read more about this in the DESeq manual. I think I will show you that before we proceed. So you can visit this page to read more about the options. All right, I'll leave the link to this page in the description box. You can also open the DESeq online resource. I'll leave all the useful links in the description box, so don't worry. I'll do that, and then you can read more about DESeq usage. Okay, so let's get back to the R environment, and then let's execute this command. Let's make sure everything is okay. Okay, that's done. So we can execute this command. All right, now everything has been done. So we can see the statistics being shown here, basically. Okay, so everything has been done. And so what we need to do is to get the results. Okay, so the differential expression result, we need to get it here. So that's get the D result. We can also say get the DESeq results. Anyhow, it's fine. So I'll say DESeq underscore results. I'll say results DDS. Now run it. So this will get me the results. Okay. Okay. We now have our DESeq results. Please take note that you can change the options in the results function. I'm using the default options, but you can change those options. Just visit this page and then you will see the various options available. Okay, so these options will allow you to even change the methods that are used for the statistical tests. All right, so the link to this page is in the description box. Now let's get back to R. So I will do this. I'll say DESeq underscore results to get the entries here. Now, this particular object here is still a DESeq object. So what I would like to do is to change it to a data frame and then I can explore it. Or let me say I will explore it. I want to put it in that format so that I'm able to explore better. So I will do this. I will say DESeq underscore results first, and I'll say as.data.frame DESeq underscore results. Perfect. So now I'll confirm by saying class DESeq underscore results. All right, it's data.frame. So now I can proceed. So first of all, let's look at the entries. Let's do a head again. DESeq underscore results to look at the entries. So we have them here. So we have the gens, and for each gen, you get a base mean, log2 4 change, LFCSC, start, p-value, p-LSL value. Let me go over again. For each gen, you have the base mean, log2 4 change, LFCSC, start, p-value, p-LSL value. All right, so we have that here. You can look at the DESeq2 documentation to get explanation for these headers. All right, so a link to all those pages and discussion box. All right, so let's proceed. Now let's do a dim DESeq underscore results to get a dimension. We have this and this. This is the number of gens, 18,314. This looks 6. All right, this is 6. All right, so this 6 here represents the headers here. Okay. So the table that we have here, we can explore it further. All right, we can also do a subset. You will look at all these things. All right, but first of all, let's do this. I want us to first do this. Let's save this to an output file. So there's the results. We are going to do further filtering. All right, but let's save this result first. Okay, so I will do this. I'll say names. I just want to get the headers again. I'll say names, DESeq underscore results to get the columns. Okay, so I have this, but then I also want to include the gen names also in this table. Now the gen names are serving as indexes. All right, but I want to include them in the main data, in the main table. So I'll create another column and then populate that column with the gen names. All right, so I'll do this. I'll say DESeq underscore results $gen name, and I'll say row dot names DESeq underscore results. I'll execute it. All right, so now if I say names DESeq underscore results, I'll have everything there, the entries here. Yes, I can also do a head DESeq underscore results to get that here. What I would like to do is to reorder this table so that the gen name comes first. So gen name, p-adjusted value, p-value, etc. I want to rearrange it. All right. So this is what I'm going to do. I'm going to use the subset function to do that. So what I will do is to say DESeq underscore results equals to subsets. And I'll say DESeq underscore results again, comma, and I'll do this. I'll move to another line, right? And I'll say select equals. And then I'll say C. Now I'll bring my brackets. Then in the brackets, I'm going to specify the columns. All right. I'll specify it in the order that I want. So this is what I'm going to do. I'm going to just do this. I'll just paste it. I have the list already here. So I'll paste it here. Let me just paste it. There's a list. All right. Let me just do it again. I think this one is supposed to be gene name rather. So I'll just type it here. Yeah. So this is a final name. All right. So we have this list here that we will use. So I'll paste everything in the description box, so you don't need to type everything again. I'll just paste it there. So just check the description box. But ideally, I prefer you type, because typing it will let you have a feel of the programming environments, and that will help you to become experienced. So I recommend you do that. Okay. So gene name, PISF value, P value, etc. So this is how I want it. Okay, so this becomes the final code or the final command. All right. So let's do this. Let's execute this command. And that has been done. So now if I say names DESeq underscore results, I'm going to get them like this, right? Okay, so this is fine. Okay, now let's do this. I want us to save this to an output file. So I'll just say write.table. I'll say DESeq underscore results. I'll say file equals, I'll say DESeq underscore results dot all dot tsv. I want to save this as a tsv file, and then comma, and I'll say row.names equals false, comma, and I'll say sep equals /t. So I'm going to save it like this. So let's execute this command. Perfect, that has been done. So now I want us to take a look at the output file. We'll come back to the R environment very soon. So this is the output file. So I'll just open it with my spreadsheet software to see the entries. All right, so we have the entries here. Okay, so everything is so cool. Okay, we have them here. You can also have another table where you combine this DESeq results with the other information, such as the count. Okay, so have the counts. So we have a gene name already. You also have the samples, and you have the specific. You can also combine them here. That's up to you. So for those aspects, I'll leave it to you. It's beyond the scope of this tutorial. So this is the output. All right. Now this has the result that DESeq2 has returned. All right. But with the statistical analysis, we have these values, PISF value. I'll focus on this one here. All right. So the PISF value here can be used to filter, okay, and get the top genes or the most significantly expressed genes. Let me just put it that way. So you can use PISF value as a criteria. You can also include log2 fold change. So for criteria, that one, you just have to look at the best practices and then use them. Okay, so that one you have to decide on that. So that's what we are going to do. What we are going to do is to filter, okay, and then select the most significantly expressed genes. We will do a subset, and we are going to save those to a different file. Okay, so that's what we are going to do. So let's get back to the R environment and then do that. So I'll just open the R. Now let's do this. Let's open R. Let's open it. Yeah, okay, we are back. So that's what we are going to do. That'll be the next step. Let's do this. I'll say extract DE genes with PISF value less than 0.05 and log2 fold change less or equals to -1 or greater or equals to 1. So this is going to be our filtering criteria. So we will issue another command here. So we will use a subset command again. So I will just say DE gene differentially expressed genes equals, and then I will say subsets. I'll say DESeq underscore results, comma, and then I'll specify the criteria. So that would be PADJ less than 0.05 and absolute value of log2 fold change greater or equals to 1. Okay, so this is going to be the final one. So the absolute value of the log2 fold change. So the absolute function here, the absolute computation, getting the absolute value, okay, will take care of both the negative and the positive values. That's what we need to. So we don't need to specify a command that will include -1 and 1. The absolute values will take care of everything. So that's what we will use. Okay, so let's proceed. So let's execute this command, and we are done. So now we can get the dim. So dim DEG, that'll give us 1491. If you take a look at the DESeq2 result itself, the unfiltered one, let me use a dim again. What do we have? We have 18,314, right? As to 149. So these are the statistical significant genes, okay? The genes which are significantly expressed. Let me just put it that way. All right. You can also go ahead. Some who may also decide that instead of using all these, they will just look for the most significantly expressed genes. So they can just use a PSF value and then sort and then pick the, let's say, top 20 or top 10. So for criteria, that one, people will have different ways of filtering. And so that one, I wouldn't go into details for that. But this is what we are going to do. We are going to order this table, what we have substituted. We are going to order it in increasing order of the p-adjusted value. So that means we are going to order it so that the genes with the smallest p-adjusted values come first, followed by those with larger numbers. And so what it means is that the smaller the p-adjusted value, the highly significant that particular gene expression is. All right, that's what it means. So let's do this. Let's do that here. I'll do the ordering here. I'll sort. So I'll say DEG equals, and I'll say DEG order DEG $PADJ. Now, ordering of tables, I've covered this in detail in another tutorial. So if you want to look at that video, check the description, but the link to that video is there. All right, so take note of that. Now we need to complete, so I have to bring a comma indicating I want to return all columns. So this becomes the final command to order. All right, so let's do this. Let's execute this command to order. Perfect. Now we can do a head DEG to get the ordering done. Okay, so this is the most significantly expressed gene. All right, so that's it. So this one, I also observed it when I ran it on the Go2R server. I also got a similar result where this one was the most significantly expressed gene. So that's it. You can also go further. Maybe you may want to do some statistics. Maybe you want to find out some genes. Maybe you have some genes of interest. You want to check their PSF value. You can also do that. All right. So that one, I will leave that to you. I will cover those in another tutorial. So let's do this. Let's now save this to an output file. So I'll say write the table, and this time it's DEG file equals the DESeq underscore, then use DEG rather. So DESeq underscore DEG.tsv. So these are differential express genes. or you can also use another name just to describe it. It's up to you. Comma, and I'll say row dot names equals false, comma, and I'll say sep equals /t. That's a tab. All right. So this becomes the final command to extract and save the significantly expressed gens. So let's execute this command. All right, that has been done. So now we can go back to our directory, and then we'll find it's there. There's it. So we can open it. That's fine. We can see the results here. So this is filtered. All right. So we have the significantly expressed genes in this table. It's also ordered, so you can trace and then look at those that are highly significant. And you can even check the log2 fold changes to see if they were up regulated or down regulated. All right. So these are things you always have to do to make your life easy. All right. So we have done that. So we now have our DESeq results. Let's get back to R. Okay. So now let's proceed. What we are going to do next is to do visualization. All right. What we have here with linear expression analysis, you will have a lot of information. So it will be easy to interpret and explain the results if you have some visualizations. As the saying goes, 1,000 words, it's worth a picture. Or let's just say a picture is worth 1,000 words. Let me just put it that way. All right. So if you have the visualizations allow you to identify patterns that can be associated with particular conditions. All right. It also allows you to do comparison of the samples or gens or whatever. So we are going to do some visualizations here as well. So let's proceed. Okay, so let's do this. Let's start. So I'll start with this one here, the dispersion estimates. So with DESeq2, you can just say plots, just ESTS, and then you can say DDS, and then main. Main is used to specify the title. Okay. So you can specify the title like this. I'll just copy and paste. I'll also leave that title in the description box as well. So I'll just paste it here. Let me format it properly. Like this. Okay. Now this list too, I'll leave it in the description box in case some of you cannot type. All right. So there's the dispersion estimate. So we can execute it, and that will give us our plots. At this stage, I'll just bring this a bit. So we have our dispersion estimates. All right. Now for the plot, I've explained them, most of them, in another tutorial. And so for this tutorial, I'm only showing you how to generate the plot. But if you want explanation, check the description box. You will find links to videos that explain the plots. All right. Now let's proceed. Let's also do this. Let's also create a histogram plot of the p-values. So we can do that also here. So with the histogram, we'll just use the hist function. I'll say DESeq results $p adjusted. So we are plotting everything. Okay, this time we are not plotting just the significantly expressed, we are plotting everything, right? And then we can add bricks equals seq 0, 1, length equals 21. Now this bricks here, okay, we are going to generate bins. So the bins will be used to represent the p-values, around the count. So here the bricks here we have 0 and 1. That means that the bin should be created, but within this range, 0 and then 1. And then we need to have 20 bins. The number of bins you want to generate, you add 1 to it. So length here is 21, but what we are going to generate is 20 bins. All right. So that's it. And now let's do this. Let's come to color. So color here, and say color equals gray, and then border equals whites. Let's bring another stuff here. So X lab, that's label, nothing. Y lab, that's Y label equals nothing. And then main, we can add our title equals. So the title to, I've already prepared the title. I will put it here. And so let me say that the codes that I'm using, I got it from the Go2R server. Okay, so when I ran the analysis on the server, it gave me some plots and I modified them. So that's what you need to know. Okay, so let's do this. Let's generate this plots. Let's first make sure that everything is okay. Yeah, everything is fine. So we can execute the scripts to generate the plots. Right, so we have the plots here. So we can see the frequencies here. Okay, so we see the range 0 to 1. And we see for the bins, we see the number of PISF values. So the number of PISF values here will ultimately represent the gens as well, okay, in some cases. Yes. So this is what we have. All right. So you can see that this plots the Y values, the axis, okay, it's up to 6,000, but the histogram, this height here is more than 6,000. So we can change the axis, the scale. Okay, so we can use the YLM option to specify the range. So I'll modify this plot. I'll say YLM equals, and I'll say C 0, 8,000, so that we can accommodate the colorless histogram. So let's execute this command. Perfect. So we have done that. So now we have been able to do that. So at least this one looks better and then presentable, right? So this is how we do. You can also add your labels for S and Y. Here we did not indicate any label. That is why there's no label here. But if you want to indicate labels, then you can just put them in the codes that we have here. All right. That's for the histogram plots. Now let's also look at Volcano plots, right? So we will do this. So with the Volcano plots, we will first set some colors. Say old.pow. So we are using the palettes. And now set some colors. I will leave all these colors in the description box. So the colors here, got them from the Go2R server. So I'll just copy and paste that here. I will just put them here. I think that'll be much faster. Again, I'll leave all those codes that I copied and pasted into the description box for you to use. So there's the color that we are going to use, or colors. We have two colors here, and those are the palettes. All right, we have them here. Okay, so we'll set the colors. We are also going to adjust the margin size in the start here. So we'll set colors and then sets margin size. Okay, so that will be par, bring the MAR equals C. That will be 4, 4, 2, 1. And then I bring my comma and I'll say 6 dot main. Let me just add it here. Equals 1.5. So the set is used to change the size of symbols. All right, so you can read more online. Okay, so we have set.main equals 1.5. Okay, so that is it. Now we need to also set the title. So let me just add that here. Set title. That will be title equals paste. We are combining everything. Okay, 2 strings. So groups 1 versus groups 2. That is TGF-beta versus control. That is what this means, right? So let's execute this command also. You execute all of them. So I want us to write the codes and then you execute everything at once, all right? Because you need to execute everything at once to get the effect. But I can also do it line by line, but I will just run them once. I will now do the plots. So I'll say plots and I'll say DESeq results $log24 change. We are plotting the log24 change and the negative log of the DESeq results the adjusted value. That's what we are plotting here. Now let's also do this. We need to add a title. So that is what I set here. There's a title, right? So I can do it here. I say main equals title. Alternatively, you can just put everything here as well, but in order not to get confused, that's why I brought that here. So if you have your own title, you can just put it in double quotes like this. Let's say title, and that's fine. But I have defined them previously here, so I'll just use that. Now, the next line, let's add X label. That will log2 FC. And then we have Y lab, that's Y label equals negative log 10. The adjusted value like this. Everything is in quotes. Take note of that because it's label. All right. So this should also be in quotes. This is it. So this should be the final comma. So everything should be in quotes. Negative log 10 p adj. All the brackets, everything should be in quotes like this. And then we add our PCH plus 20. So the PCH is used to set the character that will be plotted, right? So I'll set it to 20. We have different values. I'll leave the link to a page which shows you the different values. I'll leave all those links in the description box. All right. So take note of that. Now we need to add something else. So we'll add it here. After PCH, that'll be sex CX equals 0.5. Those are brackets. So this will be the plots. Now I want us to do the plot for this one. Okay, so we have the plots here. But with Volcano plots, it's also useful that we separate the differentially expressed gens from those that are not differentially expressed. So we would like to get colors, we would like to assign colors to up and then down regulated as well. So the next command will help us to do this. So with the next command, we are going to use this function width. So width is used to evaluate expressions without modifying the data. All right. So that's what we are going to do. So we'll add it, we'll say width, we bring our brackets, and in it we'll say subsets, and then we bring another bracket again. Okay, so just take your time and then just watch what I'm doing. Then the subset will specify this expression. So DESeq, let's call results. Let me close this space here, comma padj is what, less than 0.05, and absolute value of log 2 fc, that's full change, that one is what, greater or equals to 1, just like the expression we had previously, right? That is for it. And then we bring a comma, and then we bring another point. So we'll use the points to also highlight some values. All right. So with the points, we'll specify log 2 full change and negative log 10 padj. All right, like this. And then we bring a comma again, and we add a pch equals 20, comma, and then the color here is going to be an expression. All right, for this code too, I paid it from the Geo2R database when I ran the analysis on the platform. So I'm only adapting the codes to suit what I'm doing now. So with the color, an expression was given. So this is an expression, all right? So we will say, we bring a bracket first, and we say sign. Then we say log 2 full change. All right, like this. And then we close the bracket, which is done. And we say plus 3. All right, and we close the bracket again like this, and we divide by 2. We bring a comma and say cx equals 1, and then you close the bracket. So this becomes the final command. So here the point function will be used to highlight those values that you want to highlight. That is the log 2 full change and negative log 10. All right. So now we are highlighting them, but we are highlighting those that are differentially expressed. Okay, that is where the subset comes in. All right. So we've done the general plots, which has given us this, but then we want to color those that are differentially expressed. We want to color their respective values. All right. So that is where this and this comes in. All right. So all those that are differentially expressed, this command here will highlight them for us. All right. So that's what you need to know. And of course, we are highlighting, but we are going to use 2 colors, okay, for them. So That's what we are doing. So that is where this one also comes in. All right. So let's proceed. So let's move to the next line. And what we are going to do next is to add a legend. All right. So the legend will let us know which groups the colors belong to. Okay. With respect to the differential expressions that we have. Okay. So let's do this. So let's say legend. Let me just bring it up here rather. I'll scroll up a bit and continue. So I will say legend. And the legend should be placed at the bottom left. So we have indicated that here. And then we specify a title. So title, you will combine these characters. So paste and you say PADJ. Right, PADJ. It should be in double quotes or single quotes. Any of them is fine. I repeat, this should be in double quotes or single quotes. Any of them is fine. Then we say less and we bring our double quotes again. So this one, we are combining that with 0.05, comma, sep equals, we don't want to separate them, all right? So this becomes our title. Okay, so now we can bring a comma again. And then let's move to the next line. Then let's say legend equals C. We have down and then up like this. We close the brackets. We specify the PCH value. And then for colors, it's equals to 1, 2. All right, that's what we have here. So with the colors, we are using this one here, this and this. Those are the colors we are using. Okay, so it's all right. You can also modify the colors and see the changes it has here. All right, so you can play with that later on. Okay, so this becomes the final command for the Volcano plots. So we are going to execute this one. We already executed this, so we have to execute this also. So once we execute, we should have everything displayed for us here like this. Okay, so we have done that. So everything looks great now. So you can also save your plots. So when you go to right click, you can go to save images. But you can also save using an internal arrow here. You can specify some codes here to save it automatically. All right. So just save it. If you have any issues with saving, you can always contact me and then we can have a session. So this becomes the Volcano plot. All right, now let's move on. We are now going to do this. We are going to perform a variance stabilization transformation, or let's say variance stabilizing transformation. It's an approach that is used to generate a PCA plot. So we will do that here. So this approach has also been documented on the DESeq webpage, that has the DESeq tutorial. So you can check it out and then use that. So we will say VSD. Let me bring this down here first. So we say VSD and say VST EDS blind equals false. So we need to get the transform values first. And then we will use the transform values to generate a PCA plot. So the function for generating the PCA plots is plot PCA. And we say VSD. Then the ends group That's a group of interest equals group, right? So if you have more than one group, then you can also specify that. In the previous tutorial I made on DESeq, I had 2 groups, all right? So you can also learn how to specify 2 groups, okay, when using the plot PCA function. So the tutorial there can help you do that. So check the source when you find the link to that video. All right. So this is our final command for generating the PCA plots. So let's do that. So we'll execute it. Then when we execute it, we are going to find our plots generated. All right. Okay, the PCA plot has been generated. So we have it here. This PCA plot looks weird. As a matter of fact, I tried running DESeq2 on a Galaxy platform using the same data I'm using here, and I got a similar figure. So when I checked online, the suggestion I got was that I should extract the PCA values and then plot with ggplot. I should manually plot with ggplot. So if you also get something similar, then extract the PCA values and then plot using ggplot. Okay, that will help you sort it out. I'll make another tutorial later to demonstrate that, but for now I'll proceed with the next activity. If you also have any challenges, let me know and then we can have a session together. Okay, now let's move on to the next activity, and that is to generate the heat map. Okay, so we are going to do this. We are going to generate a heat map from the log transform normalized count for our data. We are going to visualize that for the top 10 genes. Okay, we are going to visualize the log transform normalized count for the top 10 genes. So here, top 10 genes refer to the 10 genes with the smallest PASM values. All right, those are the top genes. Before you done a subset, so we'll just pick the first 10. That will give us the top 10. Okay, now we are transforming. So we are using a log transform normalized count. So the log transformation information, I got that here from this Galaxy tutorial here. I'll leave the link to this page in the description box. So they use log 2. Okay, so I'll do something similar. So log 2, and we also have value plus 1. Okay, so I'll do the same thing here. Now normalization has been done. Okay, so why do we want to log transform the values? Sometimes it's important to transform the values because if we don't do that, then high expression values are going to dominate the plots. That will make it difficult to compare, to make comparison. All right, it will make it difficult for us to do the comparison. So it's sometimes important to transform your values so that you're able to do your comparison. All right, let's go back to the R environment and then do our exercise. Okay, so this is what we are going to do. We are first going to extract the normalized counts. So I'll say normalize underscore counts. And I'll say counts DDS normalized equals true. This will give us the normalized counts. Yes. So you can even do a head normalized counts to C for those who are curious. We have that here. You can also save this to an output file. All right, so you can do that and then later examine it. You can also subset that for the differential expressions and then just observe that. All right, now let's do our log transformation. So I will say transform underscore counts. I'll say log 2 normalize underscore counts plus 1. I'll say top underscore hits, okay, equals row dot names. Okay, now before I even do the top underscore hits, I think I'll do this rather. Let me do this. I'll run this command first. So let's execute this command. All right, And then let's do some exploration. I'll say head transformed counts like this to execute it. So we have the transformed counts. All right. So now I am going to get the gene names. Okay, so to do that, I'll say top hits plus row.names bracket DEgene 1 10. And I'll bring my comma. So why DEgene? Now the DEgene, we created it here. So that's here. That's the significantly expressed genes. We had it, we did a subset, and we also ordered. Okay. Okay, so we ordered it. So we ordered it in increasing order. So the first 10 genes are the genes with the smallest PLSF value. So that is why we don't need to do any complex activity here. We've already done some of the activities. All right, so we are continuing. So we'll do this. Let's go back. We are now going to execute this command to get the gene names. So if I say top hits, I'll get them here like this. So these are the top hits, the top 10 genes. All right. Now we need to extract their respective transform counts. So to do that, I will say top underscore hits. And I'll say transformed counts. I'll say top hits. And I'll bring a comma here. So this will let us extract the transformed normalized counts. So let's execute this command. It's done. So I can say head top hits. You get it, and it's here. Okay. Now let's proceed. Now we will do this. We are going to run Heatmap to generate the heat map. I'll say Heatmap. I'll say top hits. I will disable clustering, so I'll say cluster underscore rows pause. All right, and then I'm going to do this. I'll add an additional option here. So I'll say cluster underscore cause equals pause. I want to disable clustering. So let's execute this command. All right, so we have executed it. So we have the heat map being shown nicely for us here. Okay, so this is it. All right. So for heat maps, we can also enable clustering. You can also add annotations. All right. So I actually have dedicated tutorials on heat maps. And so if you want to learn about heat maps, if you want to learn how to generate different kinds of heat maps, then check the description box. I have links to tutorials that you can use. Okay, I have a dedicated tutorial for Heatmap. There's also one for Heatmap 2. All right, and I also have Galaxy version. So just check the description box. You'll find links to those videos. Okay, so we have it done here. In addition to the plots we have generated, you can also generate box and whisker plots that will help you to identify outliers. You can also generate MD plots, MA plots, and UMAP plots. The code for generating these plots, I mean the plots that I've just mentioned, the codes can be found in the R script that you will download. Now, after identifying your differentially expressed genes, you can also perform functional arrangement analysis, and you can also perform Keck patch analysis. So I'm currently working on tutorials for these analysis, these activities. And so just subscribe to this channel so that you get notification when I upload those tutorials. Now, if you also want to learn how to perform gene expression analysis on Galaxy, then I will encourage you to check the video right here.